Right, let's look at the idea of linear dependence and independence of vectors. Now, a set of vectors is said to be linearly dependent if one of its members can be expressed as a linear combination of the other vectors. Now, combination just means to add or subtract, and linear just refers there's no powers of the constants involved here. Okay, we're just taking a scalar times a vector plus or minus a scalar times some other vector, adding them together and seeing if they produce some other vector we're interested in. Okay, so for instance, let's take an example here. V1 is going to be this vector here with components 1, 2, and 3. V2, this one, 1, 1, there. V3 will be a vector with components 1, 4, and 7. Now the question is are they linearly dependent? Could we take one or more of those three vectors and write them as a combination, linear combination of the others? Okay, so in general, the idea of linear dependence is that you can take a vector and write it as some combination, linear combination of the other vectors. Okay, if you can't do that, then they are not linearly dependent. They are in fact linearly independent. Okay, so if we have a look here, let's take V3 for instance is equal to 1, 4, 7, and we can write that as 3 times V1 plus negative 2 times V2, so 3V1 minus 2V2, and that gives us V3. So these vectors, these three vectors, V1, V2, and V3, are linearly dependent. All right, we can't we can write one of them as a combination, a linear combination of the others. So these vectors are linearly independent. Now, if this condition cannot be satisfied, then they are linearly independent. Okay, now, so let's just start with a little bit of a condition here, but in general, a set of vectors v1, v2 up to vn are said to be linearly dependent if there are scalars dependent. If, in other words, one or more of those can be written as a linear combination of the others, then they are said to be linearly dependent if there are scalars c1, c2, cn, not all of which are zero, such that we can make this sum up to zero. Okay, when we can do that, then they are linearly dependent, because that simply means we can write one or more of them as a combination of the others. Okay, so if we take 3v1 minus 2v2 minus v3 is, well, 3v1 is this, minus 2v2 gave us this one, and minus v3 gave us this one. Add those together, we get 0, 3, 2, and 1. Okay, 3 minus 2 is 1, take 1, that's 0. 6 minus 2 minus 4 is 0. 9 minus 2 minus 7 is 0. And so we can say that they are linearly dependent because there are constants. C1 is 3, C2 is minus 2, C3 is minus 1, such that we can write those vectors together and combine them, add them to come up with a 0 result. All right, but all that just means is we've got the 0 over here, and we can simply write one of these as a linear combination of the others. So in that sense, we could write 3v1, right, is equal to 2v1 plus v3. Okay, apologies for the handwriting. All right. So you can see that v1 can be written as a linear combination of the other two. All right. I have to get used to this. All right. So basically, 3v1 is equal to 2v2 plus v1. All right. In other words, we can write this as v1 is c1 times v2 plus c2 times v3, and so on. Or v2 is k times v1. So we can pick any one of these. Because these all sum to 0, we can pick any one of them and take it on the other side. Okay, so the three statements here are just trying to point out you could pick any one of them. Like, for instance, you could pick the middle one, v2, all right, and you could take it over the other side here. Okay, and then you can write the others as a linear combination of v2. Okay. V3 can be written as a constant times V2 plus b times V1, and that's what we're trying to make out. When we can't find these constants, when they're all 0, then they are not linearly dependent. They are in fact linearly independent because we can't write them as a linear combination of each other. Okay, so let's have a look at the next section. I think we'll see an example of that. All right, so the question now is, let's deal with this. All right, can one of the vectors below be written as a linear combination of the others? It doesn't matter which one. So what you've got is V1 is 1, 2, V2 is 1, 1, V3 is 1, 4. Okay, they're linearly dependent if we can find the constants C1, C2, C3 such that when we add the three vectors together, it all goes to 0. Okay, and that it's linearly dependent because then we can grab one of those vectors, pull it over the other side, and we've got a linear combination of what's left on the left-hand side. Okay, now another way we can write this is, or constant A times V1 plus constant B times V2 plus constant C times V3 is 0, where A, B, and C belong to the real numbers. Or we could say constant M times V1 plus N times V2 is equal to V3, where M and N belong to the reals. And that's what we're going to do we're going to use that last condition there. So let's take, remember we've got our three vectors up here. Okay, 1, 2, 1, 1, and 1, 4 for V3. So we're going to say M times V1 plus N times V2 is equal to V3. Can we find some M and N, okay, which gives us this vector over here? So when we multiply M by 1, 2, the vector 1, 2, and N, the number N, by the vector with components 1, 1, well, we get the vector 1, 4. Okay, that's what we're looking for. So let's multiply the scalars out. So we get our first vector becomes M2M, our second vector becomes NN, and we want that equal to 1, 4. Now this is really just a case of solving simultaneous equations. Let me just, I jumped ahead a bit there. So M plus N is 1, 2M plus N is 4. What we're doing is equating the coefficients here. We've added these two vectors, added this one, and we've got this vector here. And we're saying that M plus N, the constants M plus N, is equal to 1. 2 times M plus N is equal to 4. So simultaneous equations. Let's label the first one equation 1, the second one equation 2. Okay, so from equation 1 we can rewrite N, transpose and have N on the left-hand side by itself. We have N is 1 minus M. Okay, and label that equation 3, and then what we'll do, we'll substitute equation 3 into 2. Okay, so we'll put equation 2 is 2 times M plus N is 4. That one there. And so 2 times M plus, where the N is, we're going to put 1 minus M, as from equation 3 is equal to 4. All right, let's expand out the parentheses. 2M minus M plus 1 is 4. Okay, gives us M plus 1 is 4. And if we go further down the page, M plus 1 is 4. So M is 3. M equals 3. So we discover what M is. Now going back to equation 3, up here, we can find out what N is. So N is 1 minus 3, N is minus 2, and so we get the scalars M and N. M is 3, N is minus 2, and what that tells us is that these vectors are linearly dependent, in that vector V3 can be written as a linear combination of the other two vectors V1 and V2 by the use of the scalars plus 3 and minus 2. All right. That's the idea of linearly dependence and independence. Remember, they're linearly dependent if one or more can be written as a linear combination of the others, and if they can't be, then it's linearly independent. Okay, now linear means there's no powers here, it's just a straight addition or subtraction of the vector, no powers of scalars or anything. All right, and combination just means to add or subtract. All right, that's it.